Hey, welcome back. In this video, we are going to be defining the undefined. We're going to be writing some definitions of our undefined terms. Now, again, when I use that first definitions word, I'm talking about the dictionary definitions of things that are undefined mathematically. And again, when I say mathematically undefined, it means that at least one of the dimensions of these three things we're going to be talking about, at least one of their dimensions is 0. So if I were to try to show this to you in the real world, you wouldn't be able to see it because it doesn't exist in three-dimensional space like we're able to see it. And that's what an undefined term means. These are just mathematical representations or mathematical abstractions. Now, it's important to understand these things because they are the building blocks of things that we observe in the real world. But these three terms themselves are undefined. All right, let's get started. The first term we're going to talk about is a point. This is the most undefined of all because it has no dimensions. It has no length, no width, no height. I can't measure any of the dimensions of a point. Our textbook says that a point is just a location in space. It names a location but has no size. If I were to represent a point geometrically, the way I represent it is like this. I show a dot with a capital letter next to it. The capital letter names the point. I can name this point whatever I want, as long as it's a single capital letter. If I run out of single capital letters, I do double capital letters. We don't name points Steve or anything like that in geometry, but I'm going to name it with a capital letter next to a point. Now, wait a second, you might say. That point that you drew on the page, Mr. Z, has height and width because I can see it's this circle that shows up on the page, and you'd be correct. But keep in mind, this is just a representation of a point, okay? It represents a location in space. You need to make the extra mental step to realize that what it's representing is just a location with no length, no width, no height. We would say that it's zero-dimensional because it has no dimensions that can be measured. What about a line then? Well, a line is that which has only length, but no width or height. That's the good Euclidean definition of a line. Our textbook would say that a line is a straight path that extends forever. We could even say extends forever in both directions. It's going to have two arrowheads on the end when we represent it. This is what it looks like when we represent a line. Bam. Notice that I have a straight figure that has an arrowhead on each end to show that it extends infinitely in both directions. If I were going to name this line, I'm going to use a lowercase letter, usually italicized, to name the line. In this case, I'm going to call this line M. Okay? Another way to name a line would be to identify 2 points that are on the line. Let's say that this point A from before is somewhere on this line. And we'll also take this point B and put it somewhere on the line. Now, I could say that this line is line M, or I could identify it as line AB. And the way I show it as line AB is I would put a double arrowhead over the letters AB. What I'm saying is that A is a point on the line, B is a point on the line, and the line connects those 2 points together, line AB. Notice that my notation again shows that it extends infinitely in both directions because I have a double arrowhead over AB. But that's the geometric way of stating line AB. You'll see me use that notation a lot this year. All right, now let's talk about some other terms related to lines and points. We could say that a set of points is collinear if that set of points lies on the same line. If I could draw a line that connects that set of points together. Here's an interesting thing. I want you to picture a sheet of paper. Maybe you have a sheet of paper nearby that you can actually do this. Now I want you to picture drawing 2 points anywhere you want on a sheet of paper. Maybe you actually want to try this out. Can you draw those 2 points on a single sheet of paper in such a way that you can't connect them with a single straight line? Like if you had a straight edge, a ruler, or a meter stick, if you need a longer one. Is there such a way for you to draw them, 2 points on a piece of paper, that you can't connect them? You'll find that you can always connect 2 points. In fact, is there anywhere in the room that you're in where you can put 1 point and another. Maybe you crumple up a tiny piece of paper and put it in one place, crumple up a tiny piece of paper and put it in another place. I want you to picture then, is there any place you could put those 2 points that you wouldn't be able to connect them with a straight line, like a piece of string that was long enough to connect them? Now, physically, there might be things that get in the way of you doing it, but you can still picture if there was nothing in the way, nothing obstructing a piece of string, any place you put those 2 points in the room, you could connect them with a straight line. Any 2 points, doesn't matter whether in a figure they're connected with a line visibly or not, any 2 points are always collinear. Any set of 2 points are always collinear. Well, we have an opposite of collinear. We could say that points are non-collinear if that set of points does not lie on the same line. And to have a non-collinear set of points, you have to have at least 3 points, because 2 points are always collinear. But let's say I take point C and I place it, about right here. There we go. Now I could say that the set of points A, B, C is non-collinear. A and B are on the same line, but C is not. What about AC? I don't have a line drawn through AC. Would AC be collinear? The answer is yes. Any set of 2 points is always collinear. In other words, there could be a line. If I wanted to represent a line connecting A and C, I could do it. That makes them collinear. Hey, can I make A, B, and C collinear? Sure I can. All I need to do is drag C somewhere where it's on the same line as A and B. And voila, I have collinear points, a collinear set of 3 points. Can I have 4 collinear points, 5 collinear points, 1,000,000 collinear points, infinite collinear points? Yes. Actually, a line is just an infinite set of collinear points. Okay, so now hopefully you understand collinear and non-collinear. Let's move on to what a plane is. A plane has length and width, but no height. So how do we represent a plane? Well, we're going to represent a plane by using a quadrilateral 4-sided figure, usually a parallelogram like the one that I have here. Okay, and what this is meant to show, there's length, like along the bottom, there's width, like along the side, but there's no height to this figure. It's just a 2-dimensional length-width figure. And this could be one that cuts directly backwards into my computer screen. It could be at an angle to the computer screen. It could be perfectly vertical up and down, but as long as it just has those 2 dimensions. So again, it's like the surface of the ceiling above you. Another representation of plane would be like a sheet of paper. Now, technically a sheet of paper has width to it, but you'd have to just make the mental leap again to imagine it doesn't have any width or height. You know, one of those dimensions doesn't exist. To name a plane, we usually use an uppercase, italicized, or script letter. In this case, I have a script N, so we would say that this is plane N. The other way to name a plane is to identify points that are on the plane. So let's say I have point D, point E, and then point F that are on the plane together. Now, we would say that these 3 points are coplanar, a set of points that lies in the same plane. This is analogs back to when we were talking about lines. Just like any 2 points have to be collinear, any 3 points are coplanar. You can't define 3 points that aren't connectable by some plane that passes through all 3 of those points. You can make a plane diagonal or oriented in such a way that it will always be able to connect 3 points together. To have a set of non-coplanar points that don't lie in the same plane, you have to have at least 4 points. So here I put G way above the plane, and that means that G is non-coplanar with D, E, and F. So we could call this plane N, we could call this plane D, E, F, by identifying 3 points that are on the plane. Now, here's the thing about coplanar points that you have to remember. These 3 points will define a plane as long as they're non-collinear. But if D, E, and F were all on the same line, what would happen? Let's say that D, E, and F all resided on the exact same line with one another. Let me just move these guys around so it looks like they're on the same line here. There we go. All right, so if D, E, and F are on the same line, do you see that I could actually rotate this plane around and still connect those 3 points? So it's important for you to realize that 3 non-collinear points have to be used to name a plane. You can't name a plane with 3 points that are on the same line. There'll be much more about that later. I just wanted to make that point now as we're talking about coplanar and collinear. In order to name a plane, you need 3 non-collinear points to define the plane. Because if I have 3 collinear points, there's actually an infinite number of planes that pass through those 3 points. But if I have 3 non-collinear points, there's only one plane that will pass through all 3 of those points. I can't define more than one plane. And again, more on that later. All right, one more term. An intersection is where we have 2 figures that meet. Could be 2 lines, could be 2 planes, could be a line and a plane. An intersection, though, is a point or a set of points where 2 figures meet one another. If we have 2 lines that intersect, like let's say I take this line P and I put it up here. See, there's my line. I better drag over my name of the line so it's clear to everybody this is line P. And let me just move this down a little bit to get a more perfect intersection. Notice that I have line P intersecting line M at point A. Anytime 2 lines intersect, they will intersect at a point. In fact, anytime a line intersects anything, it intersects at a point. Like the intersection of line P and plane N. If I have a line intersecting a plane, it's going to intersect at just one point. When 2 planes intersect each other, anywhere these 2 planes intersect, the entire width of this second plane is going to intersect the width of the other plane, and they intersect at a line. Look at the bottom edge there. That's the line of intersection that occurs between these 2 planes. In the last video, we're going to work some sample problems so you see the kinds of questions you're going to be asked based on this lesson.